Well, hello 403 class. This is Dr. Keith Schubert doing another one of our little video examples here. Today's example is going to have to do with phasors. So we'll start off by considering a simple circuit example here. And we'll consider a circuit. Let's say we stick a capacitor here, and let's say we stick a resistor here. We need some other stuff in here, so let's say an inductor and a resistor. Usually when you do these you have some amount of complex amount. This will give you your imaginary values, so we want a complex value down each line, which is why I'm doing that. Let's say there is a voltage supply here. Actually, let's do it the other way around. Let's do it that way. Driving up from here. And let's say a dependent current source. That ought to add some extra fun to it. And then we will stick, this is our outgoing circuit here. So this will be our voltage. And let's say that we want to make this one twice whatever we find going here. So we'll have some nice voltage here. Let's pick some values for things. Let's set this at 24. Let's say it's 24 volts, and let's make it at no degrees. We won't put any phase shift in at the moment. That's a simple 24 volt power supply. The fact that it is in this notation still tells you it's an AC circuit. Let's assume that this whole thing is running at, let's say, 60 hertz, fairly standard wall socket in US type stuff. Let's make the resistor here 1 ohm. We'll do book type stuff. Book type stuff always assumes nice, small, simple values, which are usually not the easiest to generate in real life, but give you some decent things to calculate and stuff. And let's make our inductor 0.0265 henries, and we'll make the capacitor similar. We'll make it 0.0265 farads. So I guess that's not the easiest. That's a 265. Now the reason why I picked those numbers, I do fully admit I have calculated those numbers in advance, because what I want is to get something that will work out nicely with our 60 hertz to give us a nice simple number. So as with test problems, things should all work out nicely on such homework problems as well. So the first thing we're going to want to do is figure out what the impedance of our capacitor is just numerically. And what we will calculate here is that this is 1 over omega times C, and omega C, omega in our case is 2 times pi times, and then our C is 0.0265. Alright, and that's 2 pi times our frequency, and our frequency is 60. So 2 pi F, and there's our C. Now the neat thing is 2 pi times 60 is 377 or thereabouts. It's a little bit less, but it's close enough. And I picked this number to be 1 over 377. So what this works out is to be a nice simple 1. Now, in particular, our 1 here is operating for a capacitor in the minus J direction. So in reality, we've got a minus J here. And for our inductor, and this is going to be equal to J times omega L. And in this case, our omega L, same thing, 2 pi times 60, 377. So you can see why I wanted to pick them to have the same number, 0.0265 for our inductor, in henries this time. When I multiply this, I end up with a nice simple 1J. And this kind of simplifies my circuit up a little bit. So what I end up with is a line here for each one of these. And this one is equal to 1 minus J, and this is 1 plus J. And then I've got a voltage source that's giving me 24 volts at 0 degrees. And I've got this lovely dependent source 2I, where I is going this way. So that's kind of my circuit that we're going through. So here we go. That's it. Now what we would like to do is first off find out our Thevenin equivalent circuit to this lovely little system here. So to do that, what we're going to do, we're going to a new sheet of paper on this one. We want to first calculate our open circuit value, the voltage for VOC. So we're going to take this and we want to calculate VOC. Now for VOC, when we are doing this, this is equal to what you get when we consider the original circuit here and we leave this open. So this is a voltage source and that's a current source. So we're going to make this kind of a super node up here. And we're just going to consider the current in and out of this super node. Now if you notice, this I and this 2I, same exact direction, which is going to give me 3I coming in, and that's the only way it can drain out down here. So this is going to be at some voltage, let's just call that V. All right. So we've got in our circuit a voltage V. Maybe I should double this up so I don't have to keep going back and forth. We're considering this is at some voltage V. So to consider the current coming out here, well, that's V divided by that particular impedance, which is 1 minus J. And that's what's flowing out. And what's flowing out has to be equal to what is flowing in. What's flowing in is this voltage minus that voltage, which means it's minus V, that's my voltage, going across this 1 plus J over the impedance. And that is then being multiplied, because I get 3 times it, 1 from here and 2 from there. So I get 3 of those. So this is my voltage for the open circuit, and I'm going to take this and then I'll take it to the other side, and I will end up with V over 1 minus J plus 3V over 1 plus J has to equal 0. And then we can just take this, factor the V out, and I get V over 1 minus J plus 3 over 1 plus J. That has to be equal to 0. Well, what's inside here is not equal to 0. I mean, you can calculate that out. It's fairly straightforward, but the important thing to notice is that is non-zero. Since this is non-zero, that must be 0. So that tells me directly that V has to be equal to 0. If I come back to my original equation, right, this was my ground, my reference. So if that is also 0, this is 24 volts, angle 0, so phasor 24. That means my VOC, which is that, plus the 24, has to be equal to 24 angle 0 degrees. And all that's saying is this is 0. I add this voltage in. That means this point, that's 0. This has to be 24 angle 0. So we now have our VOC. Yay! All we need to do for this same thing is if I find the I of the short circuit, then I can get my net impedance out of this, and I am done. So, grab another blank sheet of paper. Hopefully my wife won't kill me for stealing all of her printer paper. Okay, so now to figure out our I short circuit, what we in essence do is stick a wire across here. Now in this case, that makes a couple interesting things. That means this voltage is equal to 0. And that means this side is minus 24 angle 0. So at this moment, V is equal to minus 24 with a phase of 0. Now, from this, I can do some basic calculations. I know what's flowing out is that voltage divided by this. Okay, so we got minus 24 angle 0 divided by 1 minus J. And I also have what's coming out on the short circuit. So I also have plus the I short circuit that's coming out. That's the wire across here, because this is one big supernode again. And that has to be what's coming in, or equal to it. And what's coming in is, this is now coming from flowing up, so it's 0 minus that voltage. That's equal to 24 angle 0. 24 angle 0 divided by 1 plus J. And that is again being multiplied here, so I get twice here and once there, so I get 3 of those. I want to solve for ISC. It is now straightforward algebra at this point. So I discover that ISC has to be equal to 3 times 24 gives me my 72. Right, 72 angle 0 degrees over 1 plus J. And then we take this one to the other side. So I get plus 24 angle 0 over 1 minus J. Now there's a lot of ways you can do it. We talked about you can multiply by the complex conjugate and add it all up. Absolutely works. No problems in there. I would also suggest that you strongly consider at this point doing the MATLAB type of thing in which you can just enter these numbers directly. And you can just, say something like, little a is equal to 72 divided by 1 plus, and then you have your imaginary number J. So, we can do our 1 times J and plus 24 divided by 1 minus 1 times J. And if you actually use I for this one, it actually does give you slightly faster results theoretically, but this is so small, who cares? And then you can just do, you will get your magnitude of the phasor by just doing absolute value of A, and that gives you what's before the phasor, and then angle arctan 2, and you do the imaginary of A and the real part of A. And you'll need to multiply that times 180 divided by pi, because it's going to give you this in radians, which is the intelligent way to do it, but unfortunately we do everything in degrees because we're stuck with it historically. So this would be what I would suggest doing it a MATLAB way. It'll give you the correct answer. It's nice, it's fast, easy to do. If you had to do this by hand, then you would just do it. You have to multiply by the complex conjugate here, which means I would get 72 divided by 1 plus J times 1 minus J over 1 minus J plus 24 over 1 minus J, and then I multiply it by 1 plus J over 1 plus J. I just get their complex conjugates here. And then what we end up with is 2 on the bottom of both of these when you multiply that out. So I'll end up with this thing coming down to 36 times 1 minus J plus, and then this also ends up being 2, so I'll get 12 times 1 plus J, so I'll get 48, and then minus 24J. So you can do it that way as well, none too shabby. That gives me ISC has to be equal to 48 and then minus 24J. And you can calculate the angle and all that kind of lovely stuff off that. If you do, you will find this to be 53.7. I obviously have pre-done this one just to make sure that I had the numbers, because that I'm not doing in my head. Although I suppose you could. It's just, that one squared plus that one squared, square root being the pain in this case. And the angle, since this is in the -1, it's a negative, and it's 26.6 degrees. All right, so that gives me my ISC. So now I've got my VOC, which is 24 angle 0. Right, and I've got my ISC, which is 53 and minus 26.6. And now I can divide them. And the neat thing about our phasor notation is you can actually break it up. When I do this one divided by this one, right, V divided by I, all I have to do is divide the magnitudes and then subtract the angles, which will give me 24 divided by 53.7. Whacking a piece of paper here. Let me write this down for you. So we're doing, right, our Thevenin, Z Thevenin has to be equal to VOC divided by ISC, which is equal to 24 angle 0 divided by 53.7 angle minus 26.6 degrees. And we commented it's 24 divided by 53.7, which when you calculate that one out ends out to be approximately 0.45. It's a little bit less than that, but it's close enough for our purposes. And then 0 minus 26 just gives me angle 26.6 degrees. So that's my Thevenin equivalent circuit, which means I can take this whole complicated circuit here and I can simplify it up into a voltage source, which is just 24 angle 0. And then I can run that into my Z Thevenin, which we know is that. And that comes out, and there we go. So now I've got my equivalent circuit. So that makes it quite nice and easy to go do things. Now let's consider I want to take this, and I would like to, from this, calculate, for instance, what load would allow me maximum power transfer to the load. Now to do this, I mean, that sounds like a really complicated thing, but I picked something actually very easy for me. To get the maximum power transfer, what I want to do is pick a load such that Z of the load is equal to the Thevenin equivalent complex conjugate. So all I have to do is take that. To get the complex conjugate, you just take the actual original value and flip the angle. So that's what I picked for my load. Now from doing this, the question then comes up, how much is the actual power that I am transferring on here? Okay, now to pick what I am actually transferring, I have to actually calculate what is the current that is flowing through this whole lovely load. Current of the load. All right, this is my load. So we don't just think that's an inductor. So the current flowing through my load is the voltage that is going across it. Right? And then I need to take that and divide that by, in this case, what I'm concerned with is what's flowing through it. So I take that and divide it by what the complete impedance is that's going in here. And the complete impedance that's flowing through this is that one plus that one. So it's Thevenin plus Z of the load. Now, our voltage we know is 24 angle 0 degrees. Our Thevenin equivalent is 0.45 angle 26.6 degrees. And then to that I am adding 0.45 angle minus 26.6 degrees. Now in doing this, these ones, the imaginary components will cancel and I'll only end up with the reals. So the real part of this was, if you remember somewhere earlier back, was 0.4. You can calculate again if you want, but the real part is 0.4 from this. So I get 0.4 and 0.4. That means a total of 0.8. So that means that this is equal to 24 divided by 0.8, which is equal to 30. All right, so it's got 30 amps flowing through it. And then it's fairly straightforward from that point to get your power. Your power is just equal to the current that's flowing through the component, quantity squared, and then we have to multiply that by the load resistance. Notice I am not saying in the full impedance at this point. Power is based on what is lost, not as what is stored. So the resistance of this is 0.4, and it's I squared times R over 2. All right, so that's 30 squared times 0.2, which is equal to 180 watts. So that just gives you an example of how to do some simple calculations on our circuits here, and that gives you an example on how you can calculate things. So hope this helps a bit, and later today I'll try to do another one. Talk to you soon. Bye.